Okay, what are we doing today? We're going to review a little bit. Right? Yeah, I think, did everybody bring their electron worksheet? So let's do that first.
Right out the gate.
Stop, since that's not,
What?
that's not on the test, that stuff, right?
Yeah, there's two problems on this, on the test. That I didn't record. Well, I recorded videos for number 4, but not for number 8. You know, yeah, we gotta do it. All right.
I didn't bring
But
mine.
we're just getting, how am I'm not gonna explain it, I don't think. I think I'm just gonna do it. How's that?
I didn't bring mine.
Because I think the doing of this chemistry is more what we have in mind than the actual explanations. So what we want to do, all we're trying to do with the electrons and these numbers, and let's do the numbers again. The N number is the energy level. Energy of electron. Right? And what do we mean by energy of electron? The energy of the electron is how far away from the nucleus it is, right? The first energy level is very close to the nucleus. It doesn't take much energy to hold those electrons in place. The farther out you get, the higher energy the electron is, the more energy it takes to hold that electron in place, which means it's easier to remove, right? The farther away from the positive charge the negative charge is, the easier it is to remove. The closer it is to the positive charge, the harder it is to remove. So inner electrons, the ones that are closest to the nucleus, are harder to remove than the ones that are farther away. That's what ionization energy tells us. All right, the farther away you are, the easier and lower the ionization energy. So energy of electron is N. That's one of the quantum numbers. There are 4 quantum numbers, right? 4 quantum numbers. And N is the first. That's the energy, right? N is energy. When we write the energy level, we'll start with like a 3. So a 3 would represent energy level. So that's the example. And I brought better pens, what the heck. I mean, I might as well break one of them out instead of saving them for the summer. Yeah. So L is N minus 1 up to N minus 1. What does L represent? L represents the shape or probability of finding an electron around the nucleus. So if we said this is the nucleus, L tells us whether it's around the nucleus in a sphere, which is L equals 0 is called the s orbital, and the shape is a sphere. So if L can be up to N minus 1, the only possibility if L is 1 is 0, right? Does that make sense?
Yes.
L is 0 if N is 1, okay? If it's 0, it's the shape of a sphere, okay? If L equals 1, it's called a p orbital, and we say it's shaped like a dumbbell. If L equals 2, it's a d orbital, and the shapes get complex. And I don't even know how to describe those shapes. And 3 is the f orbital, which is way down on the periodic table in the lanthanides and actinides series, which is the second row that's removed from the periodic table, and that's an f orbital. So just knowing these letters, if I put 3p, right, that tells me energy level 3, p orbital, which means L equals 1, okay? Why we don't write 3, 1? Well, because what do we mean by 3, 1? Energy level 31? No. But they could have easily done this, but they didn't. They just call it a p orbital. And that describes the shape. Now, with a sphere, it doesn't matter where the sphere is oriented. It's going to be around the center of the nucleus, and whatever axis you use to coordinate in space where that electron is, doesn't matter because it's a sphere, so it's equally spread out around the axis. But if it's P, then you have L equal to 1, 0, and negative 1. Right? There can be 3 orientations of that orbital, or subshells of that orbital. They're all of equal energy. So if we were looking at things and we said the first n equals 1 can only have s because it goes up to n minus 1 and that gives us 0, right? There is no other choice. And so when you come down to, oh, we have the next thing, right? M sub L, right? Which is the orientation of the orbitals. So with L equals 0, no orientation. M sub L is also 0, so there's no orientation. But when you come to 1, you have M sub L being 1, 0, or minus 1. So 3 orientations, so 3 different orbitals. So 1s has 1 orbital. Now, when we get to n equals 2, L can be up to n minus 1, so 1 or 0. So at energy level 2, you have an S at lower energy, and then you have a P, right? But the P can have 3 orientations. 1, 0, and minus 1. All right? So the next thing is 2s, and then 2p with 3 different orientations, all of the same energy, right? So here we have 1, 2. So we have 3 different numbers now. Here's the 4th number, the spin number. And that can be plus 1/2 or oriented in the other direction, minus 1/2. It's not a real spin, but electrons can't have the same 4 numbers. So it has a plus spin and a minus spin. So it's just oriented differently. And the way we do that is we say, for the 1s orbital, if we put 1 electron in it, it looks like this, and then we put a second electron in that looks like that. That is now full. That's called the Pauli exclusion principle. It doesn't mean you guys don't get into Cal Poly. It just means that these 2 electrons fill an orbital, period. All right? So that's the 1s. So that's 2 electrons, 1 of plus spin, 1 of minus spin. All right. So then let's go to n equals 3. And we're going to continue this up as if it was down here. N equals, oops, not n to the 3rd, excuse me, n equals 3. Then we have, what is this? L equals what now? 2, 1, 0, right? So now we can have 3s, 3p, and what is 2? 3d. Okay? And m sub L then can be what? 2, 1, 0, minus 1, minus 2 for this one. M sub L, so let's call that m sub L2. M sub L1 can be what? 1, 0, minus 1. M sub L0 can only be 0. So we have an s orbital, we have 3 p orbitals, and then we have how many? 5 d orbitals. Right? So 1, 2, 3, 4, 5. 1, 2, 3, 1. Now something interesting happens when we get to 4. Well, L is 3, 2, 1, 0. M sub L then for 3 is 3, 2, 1, 0, minus 1, minus 2, minus 3. And then we know the game here, 2, 1, 0, minus 1, minus 2. And then M sub L1 is 1, 0, minus 1. And M sub S is plus 1/2. Oh, I forgot to do 0. Oops. M sub L, 0. And then M sub S for all of these equals plus 1/2 minus 1/2. And we do the same thing over here, right? For all of them, because that gives them the fourth quantum number, the M sub S, the spin, what we call it. Right, so plus and minus. So each one of these subshells also gets 2 electrons. So if we're filling up across the periodic table, right, we start with hydrogen. It has 1 electron, so that's the 1s, 1. So that accounts for all 4 quantum numbers. Helium adds the second one and fills the s shell because of the Pauli exclusion principle. Right? And then what comes next? Lithium. Well, if this is filled, what do? We go up to the next energy level, 2s. And how many electrons does that have? 1. What's next? Beryllium, 1s2, and then we fill this shell with its second electron. So if we were doing a diagram of beryllium, one s, 2s, and they're both full. So now we go to the next, which is what? Boron. 1s2, 2s2, 2p is the next orbital, and you put 1 in. Carbon is next, life-sustaining carbon, 2s2, 2p2. Now the difference here is when we get over to 2p2, we don't pair up first, we go across. Why? Because it costs energy to pair. So we don't pair. And that's Hund's rule. Okay? So then we're not going to be testing on that. It's all right.
Thank you, Jesus.
So carbon, nitrogen, 7, right? 1s2, thank you, Dom. 2s2, 2p3. Same thing happens. Same. Do you notice that they all feel exactly the same? We just keep adding 1 electron. All the other elements have the same number of electrons as the last one plus 1. Yeah.
So hydrogen would just have the 1 going up, not.
Yeah. Hydrogen is just 1s, so the 1s orbital just with 1 electron. And that's why hydrogen likes to lose 1 electron, right? Because now it's just a naked proton and a naked electron. Right? It also, that's why it can also act like a hydride and gain an electron. Why? Because now it's paired, and guess what? A full orbital is a happy orbital. Right? Paired up. All right, so nitrogen, 2p3. So we fill the third one. And now, the next one is oxygen, 2p4, and now we go and start pairing up again. And you can, like, I do it all different ways. Sometimes I put it above the line, sometimes I put them in the middle. Really doesn't matter. You can put a box around them, like this. Sometimes they do it, sometimes they put the box like this, label it 2p, and then make 6 boxes. I don't know. I don't do that. Oh yeah, I do. Wait a minute, I do that. And I would make 3 boxes, not 6. Whatever, that's what I do. And I did it on the answers for the exam. So, and then you go 1, 2, 3, 4, 5, 6. Okay, that's called the box diagram. What else? So those are the 4 quantum numbers, how they work. What happens with 4 that was interesting, and get back to that, is that 4s, these energies start getting closer together when you get farther away from the nucleus. So it turns out you fill the 4s before you fill the 3d. That's the quirky part, right? And because it's a little bit slightly lower energy. All right, so that's where we are on that.
How would one like tungsten?
How would tungsten look? All right, well, let's get to tungsten then. What number is tungsten? What's the atomic number of tungsten? Should I leave this here, or can I erase, or? What was that, Adrian?
You can erase it.
All right, so tungsten is what number?
74.
74? Good Lord.
Would we start with our noble gas?
Yes, so there's a shorthand. Thank you, Don. What's the shorthand? Shorthand is is the noble gas that comes immediately before
Xenon.
xenon. Before the metal you're looking at, or the transition metal in this case. So xenon, which is what number?
4. Oh, sorry, 36.
And it's the end of the fourth row?
Yes.
So when we're at the end of the fourth row, we go to 5s2. And now we're in the D block. D block is always one level down, as 4s then 3d, well, 5s then 4d. And 36, 38, that's the last one. Uh-oh. I don't think xenon's the right one.
What are we looking for?
Yeah, for tungsten, if you want to, if you're okay with
Oh, it's 54, not 36?
50. Oh, yeah, I read one up. I apologize. 54.
I'm just accepting random numbers, and no one's correcting me except, thank you,
I'm
Nate.
glad you trust
Just
me
make
with
it-
my numbers.
Well, now I'm not. That's what I get for having you here all semester. I start believing you. 54, and not believing. I'm like, that's not right. 54, 56, 66. Where are we? 66, and then 5p. Is that right? No, tungsten's. Let me see that. Let me see that. I do.
There we go.
Where is it? I don't know where it is. You
What,
said
tungsten?
yeah,
74 is way equivalent.
right there. Oh.
Oh,
So this is 6.
yeah.
Yeah. So let's
So it's not.
go there. Let's go here.
Yeah.
Row 6, because 30.
Did you introduce a new letter?
Yeah, new letter. So where are we now? 16, 60, 70. Where were we? 5, D, 4. Turns out that the preferred method here, because of the overlap and closeness and the fact that half-filled orbitals are preferred, this is an exception to the filling rules. So that is the electron configuration for tungsten. Now, if you have tungsten 4 plus, let's say if you had tungsten 3 plus, all that goes away, right? We still have the xenon, all the electrons that fall before xenon, and then you have your 4F14, you have your 6S2, and you have your 5D. We're going to take away 3 electrons, right? But we already took away 1, so is that right? 71 should be. 54, 58, 71, right? So that's the 3 plus. What happens? You take away 3 electrons. And because these are individual electrons, now all of a sudden it's preferred to overcome the bonding here because we're losing electrons in the d orbital and it's not half full anymore. right? So that's the half full exception for d orbitals. Also, if you go to d10, it's the same thing. So that was, we kind of jumped from intro to advanced right there, but that's where we should be anyway.
Why do you do those exceptions, just so you could have it at least half full?
Right, so energy levels of a half full orbital, like D5, are preferred over S2, D4. Right, the pairing energy is less than it is for the half full energy, so we're at a lower state. It costs more to pair it, so it doesn't pair. But the minute you get to 6, now it pairs up, and then you go on about your business, electron-wise. And it's important when you're doing minute things like when you're trying to put gold atoms on top of a silicon chip. It makes a difference whether you're D5 or what your energy level is. Okay, so what does that have to do with what we're doing here? Okay, so we're going to do the same. We're going to do the sodium. I think that's page 1, right? Sodium orbitals. So sodium plus is the first one. So this stuff helps you with problem 4, I believe. The legend helps you with problem 4. And then what I just did helps you with the question 8, I believe. There it is. No? Red. Where's the board? Come on, board. Come on. There you go. So sodium, Na plus, which means it's gotten rid of 1 electron. So we have 1s2, 2s2, that's 2p6. Now we're at 10. Oh, and it did have 3s1, but we lost that electron. So to draw the diagram, 1s, 2s, 2p, and we're just going to fill 1, 2. Fill the lowest energy level first, which would be 1s. That's the Aufbau principle, which is German for lowest first. And I'm going to put all these in because I know they're all full. Right. And that's sodium plus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Now chlorine minus. So the anion, right? We have 1, what would that be? 1s2. So energy level 1, shape 0. Energy level 2, L equals 0. Energy level 2, L equals 1 with 7 electrons. And then we're going to add 1, so 8. Oh, we can't do 2p8, can we? 2p6. Oh my gosh. Where is chlorine? Oh, let's see. 17, right? Is it, what is it? 17. So 18, right? So where are we? We're at 10, 3s2, 12, 3p6 is the minus. So 1s2, right? 2s, 1, 2, 3. I like when you guys correct me. It's almost more fun to make mistakes than it is to do it right. 2p6, then 3s, 2, 1, 2, and then 1, 2, 3, 3p, 1, 2, 3, 4, 5. That would be our 7, and then here's our 8, and that's chlorine minus. So the electron configuration, and circle the valence electrons. E minus configuration. Oh, I did those already, right? This is the electron configuration. That's what this is called. And that's just listing what the orbital diagram in numbers in a sequential fashion. Give the electron configuration of only the valence electrons. Okay, so valence electrons are the ones that are the farthest from the nucleus. Yes? Valence electrons. We recognize them because they have the largest N value. Anything that has the largest N value is the valence electrons. All of the electrons in that energy level have count as valence electrons. Everything else counts as core electrons. Why core? Because they're hard to remove. Why? Because they're closer to the nucleus, takes more energy. And to use that kind of energy, you can't really do any chemistry because it comes apart. So 3s2, 3p6, that would be 8 electrons in the valence shell of chlorine minus 8 electrons is stable. That's why chlorine wants to be a minus 8. Really? It's always something. Okay. So give the electron configurations of only the valence electrons. So how do we know what the valence electrons are? Well, we look at our periodic table. Don, man. Right. And this is why we call column 1 and 2 the S block. Column, what is this? What do we call this now? We call it 13 through 18 the P block. Call these the D block, the purple, right? And then the energy levels right here. So if we come down here to row 6, everything in the 6th energy level is a valence electron. So if we're right here at calcium, we're at 6s1, we have 1 valence electron. Right? By the time we get over to, let's stay in that row. What is that? I can't even read it. Oh God, I need glasses. Radon, right? The deadly gas, the silent killer. You're at 6p6, right? Plus 6s2, so 8 valence electrons. And then any number in between, right? But when we go to the D block, those aren't valence electrons until you get rid of the S block. Okay, so what are we looking at now? Valence electrons for sulfur. What row is sulfur in? What column is sulfur in? It's in the oxygen column, right? Oxygen, then sulfur. So 6 valence, column 6, so 6 valence electrons. The top number in the old days represented the number of valence electrons. So sulfur 6, sulfur 2 minus, we take the 6 and then we do what? We add 2 electrons, so that's 8 valence electrons. Is that right? Yes, of course it is. And then potassium is in column 1, so it has 1 valence electron. Calcium plus has 0 valence electrons. And S2 resembles what noble gas? S2 minus. What's the one below neon? Argon. Lots are gone. Argon, right? Because it has the same configuration. You go over 2 electrons, that's the argon configuration, correct?
Yeah.
Woohoo! Thank you for that. I love that. K plus resembles which noble gas? So it's going to go backwards from potassium to argon. Apparently that's the answer of the day. Right, so potassium losing 1 electron and sulfur gaining 2 electrons give the same noble gas configuration.
Does it just depend on how close it is to the other one?
You mean whether they gain or lose electrons? Or whether which gas it?
Which gas it would be closest to?
Well, it would mimic the gas that has that same electron configuration. If we're using the shortcut, you couldn't use the shortcut with sulfur. You'd have to use you'd have to use neon plus the electrons that follow neon. You couldn't use them.
Oh, okay, never mind. I
Right, that's what you were thinking?
I was not noticing the electrons, the
Oh, okay.
ionic.
Oh, right, okay, yeah, the ion the ion configuration is what we're talking about, not the shorthand. Okay, so two different things. When you gain or lose electrons, you revert to the noble gas configuration you're closest to, because that's the most stable. When you give the shorthand using the noble gas, it's the previous gas plus the electrons that follow. Okay, S2K plus and argon are said to be isoelectronic. That's a nice word, because they have the same number of electrons. Name two other ions that are isoelectronic with them. So what comes after potassium? Calcium? Is that right?
Yeah.
So calcium's one of them, calcium 2 plus. And then what comes after sulfur? Or what?
Chlorine, so it'll be chlorine one minus.
Yeah. There you go. All isoelectronic. Are scandium 3 plus and chlorine isoelectronic? That's some kind of guessing.
Technically,
I can't see.
do they have to share the same?
I don't remember
noble gas?
as well as I used to.
Because they both relate to noble gas, but it's not the same noble gas.
If it's not the same noble gas, then you're not isoelectronic.
Okay, then no.
I don't even. Oh,
There we
well, it's isoelectronic with the other ones we were talking about. And then
Yeah.
what was the final
go.
one?
But not with each other.
Oh, yeah. Yeah, they are. Yeah, yeah.
Wait,
Yeah.
Yes. You lose 3 electrons from scandium, you go to argon. You gain 1 electron from chlorine, you go to argon. So therefore, they're isoelectronic. Okay, and then bromine 1 minus and sulfur 2 minus. Are those isoelectronic?
No, they're not.
Okay. Oh, we're almost through with the first page. Awesome. Is silicone paramagnetic or diamagnetic? Uh-oh. So we didn't talk about that. What's the atomic number of silicone? 14? Oh, good. So we know that we now know this is 10, 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and a blank. So, when electrons are unpaired, you can take advantage of all kinds of properties. That's called paramagnetic. When electrons are paired, like in helium, diamagnetic, right? Paired different magnetisms. Dia, 2 magnetisms. Para, 1 unpaired electron or 2 unpaired electrons. Doesn't matter. As long as they're unpaired, there are magnetic properties associated with that element. We use that to take advantage of. I actually got a paper out of paramagnetic hydrogen. Who knew? Right? I got all excited about working in Rochester because they had so much money. It was fun because I got to play with all kinds of toys that I assumed were in every department in the United States. They're not. All right. So paramagnetic. How many unpaired electrons does sulfur have? Well, sulfur has, we learned sulfur has 6 valence electrons. So let's just look at the valence shell. There's 2. 4, so that's 6. So this is 3s, 3p. How many unpaired electrons does it have? 2. Yay. So it's diamagnetic or paramagnetic? Paramagnetic. Very good. Circle 1. Don't circle both of them. Well, many unpaired. Or circle one and erase it and then circle the other one. That's what I see a lot. And usually it's the first one that's right. Unpaired, how many unpaired electrons does chromium atom have? Oh, chromium's one of those ones, right? It's a D5, S1. So how many unpaired electrons does it have? It's, what is it? Chromium's 24, right? Oh my goodness. Oh, let's go over here. We've been over here for a while. Hi, Maria. What row is chromium? 24. So 1s2, 2s2, 2p6, that's 10. 3s2, 12. 3p6, 18. 4s2, 20. 3d4. But we know that's not good. So we do 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5 because it's half full, right? Because there are 5 3d orbitals, and you want 1 in all of them because a half full shell is better than a paired, what? 4s. So 1, 2, 3, 4, 5, 6 unpaired electrons. Which is why chromium, it can be very reactive. We can even have chromium 7, right?
Extra shiny.
Extra, we don't like it, extra shiny. Yeah, right, that's our bump, that's what bumpers used to be. Like you get a 50, I saw the nicest 56 Chevy pickup today. And the only reason I saw it was because the guy was parked and the blinker was still on and he wasn't in the car. Beautiful, nice old man, he was at Andrews, he was a very nice old man. And we chatted about his awesome truck. There's room for him, if there, you know, I got that property, I could just dig another hole, put him next to one of my students that I constantly am threatening to bury, and I could have his truck.
Recording.
If
Oh,
the
it
world,
is.
I didn't name names, if the world
It
was
is.
run that way, if I didn't follow all the rules to a letter, and I would never threaten anyone with physical harm and mean it, because that would mean that I would be reported and have to spend time in lockup.
It's not worth it.
It's not really worth it,
It's not really
right?
worth it.
I love my life, I like walking around.
I love
being
my
outside.
life.
How do we know it's you? I think somebody's admitting to that. Let's keep moving though.
Yes, sir.
You know, and there'll never be another class with that person in it, in my videos.
Cause they'll be
I know
dead.
you'll miss me.
Cause they'll be dead.
I'll miss you, Dom. All right, but, because he's got a bitchin' Mustang, so, you know. Got a Mustang and a truck, I have a fleet. Yeah, there we go. So the next one is just the next one is you guys can fill in the blanks, right? Because we know the rules. Fill the lowest energy orbital first, right? Fill equal, which is off-bow principle. Fill degenerate orbitals, which are energies of the orbitals are the same, before pairing up. That's Hund's rule. Only put 2 electrons in an orbital, which is the Pauli exclusion principle. So let's do that on our own. And what else do we have to do? Oh, change, once we get the numbers there, just write down 1s2, 2s2, and just follow the orbital diagram, because that's the orbital diagram, that's page 2. So I think we can all do that. I mean, you don't have to do it. Let's look at the next thing. The end numbers. This is a good one. Right, this is more of what we started with in the lecture. What was that, Sid?
Your pages are different.
Yeah, our pages
They're the
are all over
same,
the
but you
place.
must have it stapled a different way.
We are all over the place.
We'll blame it on the stapler. I was gonna say that.
Yeah, it was the staple person.
I don't know.
Just another reason on the long list of, yeah. Mine's not stapled. I have, you don't have, this is page 2, vanadium and all that?
Yeah.
It says page 2. Oh, but the sodium chloride wasn't page,
That was the last.
Yeah, that.
oh, that's the last page. Well, I did the last page first. How about that? Okay, that wasn't operator error. Okay, we're on page 2 is the one I'm talking about where you can fill it in yourself. With vanadium, arsenic, chromium, the exception, which I just did right there. And look at that, it came out the same. 6 lone pair, who knew? Yeah, all right. And then copper's also an exception. So we know what that exception means. It means we're gonna do a half-filled orbital, right? Something, or a full orbital. Joules? Are we doing kilojoules today? Well, joules? That's like me saying I'm gonna do it. You can't be saying that.
It's just asking if the s orbital for copper is gonna be empty, so the d orbital's gonna be full.
Yes. So as Jules points out, for copper, we're gonna fill the d orbital and not put any electrons in the, no, it has one. It has one in the s, right?
Whatever.
1, 2, 3, 4. There's one in the s.
All the way to.
Oh, they said, don't damage my jacket, it goes on like this.
No, zinc is S2D10. This is S1D10. All right, so those are that. Then let's look at page 3 then, shall we? We got lost there for a second with all the talk about violence, which there's no room for violence in chemistry, except for the biggest explosion and most death ever in history was caused by chemists.
Wait, you said that the valence electrons are the ones in the last block we put the thing in, or what?
The highest energy level.
Okay.
So, for example, if we're talking about copper, then it's, what is that, the 4s? Or is it the 5s? It's the 4s, right? You only have one electron in the 4s, you have the D10 filled, but D10 is the lower energy. But if you took the one electron away, now you would have 10 valence electrons. Yeah. Okay. Good answer. Great question. So let's look at page 3. Yeah, they do the apartment building thing. I'm thinking of using like colored shoe model, right? You have a shoe place and you put it in the shoe box and the red one goes here and then you pair up the red one and now that box is full. Then you go to the blue shoes, but you have 3 blue shoes, 3 sets of blue shoes, so you put the blue. Is that a good, does that work?
Yeah,
What?
That makes sense.
Yeah.
Right, and then it's stacked, right? So each row is a different energy level. And you have your like your cheap black pair, your nicer black pair, and then your nicest black. I don't have a lot of shoes.
Your Nike versus Jordans for sure.
Well, see, and it even works for guys. So there you go. If you're the kind of guy that has more than one pair of shoes, God bless you. All right.
Your dogs versus your pockets.
You talk about privilege.
Yeah.
Multiple pairs of shoes.
Oh my God, I have a.
Right, I used to duct tape my shoes because I missed out on that whole privilege part. Oh wait, that's a comedian. I'm just mimicking a comedian. I didn't miss out on it. I'm sorry. I had a great life, and I still do. So I wish I could help others more. Okay, so what element is? I keep saying that. What element is shown by the ground state orbital diagram? Oh my God. So there are 32 electrons there. What is 32? I just did a quick count. 2, 10, 20, 32. Which is what?
Germanium.
Yes, it's germanium to this discussion. Okay, so 32 electrons. Give the quantum numbers for these 6 electrons. And then there's a little arrow going there. So the N number is what? 3. Okay. The L number is page 3. Page 3, problem 2. And problem 1 is 32 electrons or germanium. Problem 2 says give the quantum numbers for these 6 electrons. It's listed 3p, which makes n equals to 3 and L equal to 1, because p is 1. 0 is s, p is 1, d is 2, f is 3. So L is 1. Then M sub L is the number of degenerate orbitals, which is L positive to L negative, which is 1, 0, minus 1. So that's M sub L. And then for each electron in each of the degenerate orbitals, or the one, let's call it like it is, N3, L1, M minus 1, MS plus 1/2. And the second electron is the same, 3, L1, minus 1, minus 1/2. And then 3L0 plus 1/2, 3L0 minus 1/2, then 3L minus 1 plus 1/2, 3L minus 1 minus 1/2. Okay. Number 3, give the quantum number for these orbitals. And it's the 3D. I think, oh no, which one is that? Oh, L equals 1. Okay. We already did that. Okay.
it's the 3D.
Oh, it's a 3, oh, yeah. I drew a line that made it not look, because I did the one for 5. All right, so yeah, 3D, which makes L equal to 2, right? Because the shape of the orbital is the L number, right? So S is 0, P is 1, D is 2, F is 3.
Explain the 1/2 and a 1/2 side.
Right, so that's the spin, right? It's not really a spin, it's just the orientation of the electron. There are 2 electrons. They can't exist as with the same quantum numbers. So we say one is facing this direction electromagnetically and the other is facing the other. So we give them these things, imaginary things called spin, and we say one's plus and one's minus. So each electron in the pair is essentially having a dipole facing one direction and one facing the other. It's how they can be close together.
So if there's
In
2
the
in
orbit.
one block, you put it's minus 1/2, or? I don't get
No. So the first one, if we have an s orbital, that's 1 s, which is the n number is 1, the L number is 0, the M sub L, which is the orientation, is 0 because it can go anywhere, and then the first electron has a spin of plus 1/2. Whoa, what numbers are those? I've been going too long already. And then the second electron has 1s, this is 2, this is 1, the second electron, N1, L equals 0, M sub L is 0, and the spin of the second electron is minus 1/2. And that's how we pair them up, because they can't have the same 4 quantum numbers be equal, because that wouldn't describe a different electron, that would still describe the first electron. So in order to separate them, we use the spin orientation within the orbital.
So for number 2, it's minus 1/2 for that answer?
No.
You would write exactly what you put there, right?
For number 2,
How would you
Or
write,
you put
write on
both
the
of
board?
them? Yeah.
oh, I see. So for number 2, you
you
write n equals 3, right? So, yes, we have 3 degenerate orbitals. L equals 1, because 3 degenerate orbitals, the shape is the P, P is L equals 1. So minus L, M sub L, well, let's see, M sub L is 1, 0, minus 1. So each one of these orbitals has one of those values. Yeah? So then the spin, if we put 1 electron in here, is plus 1/2. When we put an electron in here, you'd probably call that first one 1, and then you do it n equals 3, L equals 1, M sub L equals 0, and then M sub S equals plus 1/2. Then you do the third electron the same way. N equals 3, n equals 3, L equals 1, M sub L equals minus 1, M sub S plus 1/2. And then to differentiate, you do the same thing when you pair up, but now you're adding a spin quantum number of minus 1/2. Here, minus 1/2. And then when you pair this one up, also. And you can do this arbitrarily, either one, either way.
So
Right?
I'm supposed to put all of that in the little,
Can you just put like a comma? you put
I just
plus
put
one
n
half,
equals
comma,
3, comma, L equals 1, comma, M sub L equals minus 1, 0, or 1 minus, 1, 0, minus 1, and M sub S equals plus 1/2 and minus 1/2. And then the quantum number for the orbital in 3 is 2. L sub, the quantum number of L, right? Oh, it says give the quantum numbers of these. So L equals 2, M sub L equals 2, 1, 0, minus 1, minus 2, N equals 3, and M sub S equals 1/2 positive, 1/2 negative. Give the quantum numbers for each of these 2 electrons. So this time I just wrote N equals 2, L equals 0, M sub L equals 0, M sub S equals 1/2 positive and 1/2 negative. Are you guys with me on this? Is that, can you see it? No, you're not with me. All right. So for the 2s orbital, and let's get off the green again, because I don't know why they even include green. I'll teach you guys to let me miss a class. I'll fill these time things we don't need to do. All right, so 1s. Oh, we're not doing it. We're doing 2s. All right, so we have 2 electrons in the 2s. Okay, Dom, what is the n value?
Say it again?
What is the n value?
Two.
2s is 2.
2. So n equals 2. Now, the L value is represented by the letter
Yes. So that's
0. All right. M sub L can be L to minus L. So 0 to minus 0. So M sub L, or the orientation of the orbital, is 0. And now for the first electron, this magnetic spin number is plus 1/2. If we're going to add a second electron,
minus 1.
it's minus 1/2. Yeah?
Yes.
Okay. So that's how we describe each one. There are 4 quantum numbers. The n number, which is the energy level, which comes first. The s number, the s letter, which represents L, which is the shape, right? So 2s, if we did 2p, L would be equal to 1. And then M sub L then is equal to 1, 0, and minus 1. So 1, 2, 3, right? And then we can break that down for each of these orbitals, right? So then, now we have 3 of the quantum numbers, which n equals 2, L equals 1, M sub L equals 1, and then we say, for the first electron, plus 1/2. And then to keep track of the second electron, now we're gonna move over and say L equals 0. And then for the third electron, we're gonna move over and say L equals minus 1. Right? Or M sub L, I should say. Sorry about that. Scratch that. Put it where it belongs, right here. M sub L. It's always me putting things in the wrong place. All right, M sub L. What did we do? Minus 1. Oh, we did 1 there. And, right, so the second electron would be M sub L equals 0. The third electron, M sub L equals minus 1. And then, of course, each of these, plus 1/2, minus 1/2. Right? So 1, 2, oh. First one, we're all going in the same direction. The second electron then is going to have the other quantum number of m sub s equals minus 1/2. So always 4 quantum numbers to describe it. No 2 electrons have the same 4 quantum numbers. That's the point. And why does that happen? It happens because we have to label these electrons around the nucleus. And the closer they are to the nucleus, the more defined that energy is. As we move farther away, there are more possibilities to find where the electron is and is not, right? And that's why we have these defined shapes. And remember, it's not actually where it is, it's the probability of finding it in that space. And we have 4 places that we define by those numbers. Okay, that's that. Okay, so is that a little bit more clear, I hope? If not, I really don't have another way of describing it at this point, but I can try later. Where would you find the electron with this set of quantum numbers, n equals 3, L equals 2? What is the L equal to? That's the d orbital. There's only one d orbital here. Okay. However, right, there are 5 locations for m sub L that it could be. And so m sub L equals 0. That would be the middle one, right? Because if you have 3d, right, so that means n equals 3, L equals 2, m sub L then is the 5 orbitals of 2, 1, 0, minus 1, minus 2. So 0 would be in the middle of the 5, in the way I think of it. So I would circle this one for number 5. Number 6, what are the possible values of m sub L for electrons with n equals 3? And the L's were all written right here, by the way. One last day talking out loud. Very nice. And then I get some time off to heal. Okay. And so do you. I mean, you guys need it more than I do. I'm just up here just spitting stuff out. N3L is 1. So what are the possible values of m sub L? Well, L, 2, minus L. So if L is 1, that's 1, 0, and minus 1. Yeah? Okay, what's wrong? 7, what's wrong with this set of quantum numbers? N equals 2, L equals 2. Yeah, L has to be 1 less than N, so L can't be 2. How many electrons can have N equals 3, L equals 2, and M sub L equals 1? That defines an orbital, so how many possibilities are there? 2, thanks, Jules. And what is the maximum number of electrons that can have N equals 4, L equals 3? N equals 4, L equals 3. That's an F orbital, and that means M sub L, or the orientation of each of these orbitals, could be 3, 2, 1, 0, 1. Minus 1, minus 2, minus 3. So 1, 2, 3, 4, 5, 6, 7. And that would be 2 in each one of those. 14. And where were we? What is the maximum number of electrons that can have n equals 3? Let's go over here. We haven't been over here in a while. I want to make sure Maria doesn't fall asleep while she's doing this important work for the betterment of mankind and missing work which actually is for the betterment of mankind. It's a little weird, but it's the way we do it in this world. Ooh, and I just painted my face blue. Awesome. Okay. What number is this? This is number 10. N equals 3. So when n equals 3, L can equal 2, 1, and 0, right? And then what else do we have? Oh, it gave us more. It gave us more, didn't it? No, just n equals 3. So let's see. When m sub L then is 2, 1, 0, minus 1, minus 2. When m sub L is 1, or minus 1, and then m sub L is 0. So 2, 6, 10, 18 electrons. Because each m sub L is a suborbital. Each suborbital can have 2 electrons. So 18 electrons. Number 11. What is the number of electrons that the ground state of phosphorus has with n equals 3 phosphorus, which is what number? So n equals, what is it? N equals 3, L equals 1, which is the p orbital. Oh, with n equals and L equals 1. So how many electrons is that? 2. Oh, do we know that? 15. Uh-oh. Do we know what that is? 2, 4, 6, 8, 10, 12, 15. Ooh, tricky. Only 1, because they're not paired up. Tricky, tricky. That's why you got to do the orbital diagram or the electron configuration. Okay, and then we play the guessing game. For each of the following sets of quantum numbers, state whether it is loud. Everything I say is loud.
This was the next one 0?
Oh, I didn't do the next one.
There's N3,
L is 2. Yeah, we don't have any d orbitals, do we? So it's 0. Sorry, I missed that one. I didn't see the little. Well, fortunately, it won't be my problem. Okay. Each of the following sets of quantum numbers state whether it is allowed. And again, I'm loud. So, does that mean I'm allowed? Aim allowed? That's a chemistry joke there. So n equals 4, L equals 4. No, because L has to be 1 less than 4. N equals 0, L equals 0. Nope. N equals 3, L equals 2. Yes. M sub L minus 2, yes. M sub S plus 1/2, allowed. I didn't hear anyone though. You guys were not allowed. You were quiet. Okay, and we only have like 5 minutes left. Awesome. N equals 2, L equals 0, M sub L is plus 1. No, M sub L has to be plus or minus L. And plus 1 is more than 0, so. All right, and we covered that whole thing, and now we don't have to do it in lab. Oh, no, we didn't cover the whole thing, because we have page 4. Okay, this is valence electrons. This is going to go fast, right? The largest N number, which would be in the first one for carbon, is what? This is where you say things aloud. 2. So how many electrons are in the 2 level for carbon? Anyone else? 4. Correct. You gotta stop answering. So it's like it's like we're having a conversation and everybody else is excluded, which would be fine, but we're not. That's not the goal. The goal is audience participation on the last day to buffer you from the final of 200 points, right? Some audience participation. So, what about nitrogen? Highest energy level. 2. Thank you.
2.
Thank you. Appreciate that, Maria. Right, so there we go. 3 people out of 20 something.
Yeah.
All right, so how many electrons in that level? 2 plus 3, 5. Oxygen, same again, 2. So 2s2, 2p4, that's 6. Fluorine. Oh, we should be writing down the electron configuration. My bad. You don't have that in front of you. Oh yeah, you had it in front of you for the first 3.
Yeah.
Right. So for the fourth one, we're just going to add 1 electron. So 1s2, 2s2, 2p5. And 2 being the valence shell, 2 plus 5 is 7. Going to neon, the noble gas with a stable configuration of 8 electrons. So I didn't even care. It's 8. And guess what? The group numbers match the number of valence electrons. All right. Chlorine 17. So 1s2, 2s2, 2p6, 3s2, 3p5, 7 electrons. 7, and it's in the 7th column. Very good. And then we're not doing valence electrons for chromium or copper, but we already did their electron configuration. Now we're just writing it down from the previous one. And then ytterbium, 3 plus. That's a pain. I'll give you that one. 1s2, 2s2.
Which one is that one?
The last one. Or is it yttrium? I don't know. I never remember which Y.
1s2,
2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Okay. And then give the electron configuration following using the core noble gas configuration. So for phosphorus, it's neon, right? 10 plus, we have to do 5 electrons, so 3s2, 3p, oh, it's 3 minus. We're good. So neon, 3s2. Neon in brackets. If you don't know what that looks like, so you go to the last, so for phosphorus 3 minus, you look at the configuration of the last noble gas, which is neon, right? Which has 10 electrons. Phosphorus has 15, but when it's 3, didn't do that right? 3 minus, not 3 plus. Bah. So neon 4s2, that's 12. 4p6, that's 18, and this is 18. So I would have got that one wrong because I would have gone the other way, made it 3 plus. But it's actually 3 minus, so we're adding 3 more electrons to the 15 of phosphorus to make it 18. So we have to count for 18 electrons. So we do that we take neon, which has 10 electrons. Is there anyone following this at all besides
Yeah, it made sense until this one, this didn't,
All right.
I didn't understand none,
Any of that part?
any of that part.
All right. Whoa, it's jiggling. Got a little rhythm going there, that's good. Uh-oh. Oh, come on, we're almost out of time, almost out of time. All right, so our time together is coming to an end. Sad. Oh, not yet, Jim.
So are we not reviewing?
I guess we'll review in lab if you want to. Phosphorus, what number is phosphorus? Brittany,
here.
since we'll just do one last thing with Brittany, just the way we
Fif-
open the class to end the class.
15.
15. Okay.
15.
And what noble gas comes before phosphorus?
Yeah.
Which is 10.
Is your name Brittany?
Oh.
Which is 10. There you go.
Brittany too?
Class participation.
Okay, so we're gonna use the configuration of neon to
Mhm.
account for electrons, because everything that comes before on the periodic table makes up the next electron configuration of the next element.
Okay,
So neon accounts for how many electrons?
10.
Okay. And then what's the next energy level after neon? So if you go to neon and then go down a row, what's the next row?
Argon.
No, that's the next noble gas. What row comes next?
Letter.
Number.
Umbrella.
That's true.
Lori. I don't know. I have no idea.
3.
Yes.
And then we start with S,
Mhm.
so that's 2. And then we go to P, 3S, 3P. Let's see, where are we? We're at 12, 13, so we need 3 to make 15. You with me now? So far?
Yeah, sure. I don't-
Okay.
I don't-
And then we add 3 electrons, and then we get neon.
I'm not.
3s2, 3p6, because we're adding 3 electrons to this. So if we were to look at this, 1s2, 2s2, two p6, right? This configuration is neon. Now, when we go to 3s2, 3p1, 2, 3. This is ground state phosphorus. And then we're gonna, because it's 3 minus, we're gonna add 3 more electrons. 1, 2, 3. And so now we're at neon configuration, 1s2, 2s2, 2p6. And then we have to account for the electrons that come after it, so we call it a shorthand. And then we just count up the electrons, 3p6. Which is also argon, isoelectronically.
So just to double check, when there's like a +3 key, you just add that to the last exponent, whatever it ends on?
3 minus.
Oh, 3 minus, yeah. my
Yeah,
bad.
but if we could easily do this too, which would then be the neon configuration. And then since we had 3p, right, now we're gonna have, since I added, but let's go back to that. We have 3 electrons and the plus, so now we're gonna take them away. So we have 3s2, and now we're done. That's what I was gonna do the first time because I wasn't paying attention. Yeah,
How are we getting the number of valence electrons so fast? You said for carbon that there were 4.
right, so you go to the top of that chart, it has a number 4 up there. That's one way.
Okay.
The other way is that if we look at the periodic table,
Okay.
the other way is if you look at the periodic table and you go, everything in this row, in the S block or the P block, are valence electrons. The D block isn't because it's one energy level behind. So if it's here it's 1, if it's here it's 2, if it's here it's 3, 4, 5, 6, 7, 8. Thanks for your patience.
If you were gonna get a question like this, would you have the orbital diagram blank and we fill it out, or would you want us to actually draw the orbital diagram?
Yeah, I'm gonna have to give it to you. I was having it blank, but we don't have enough experience.
So number 8 on the practice test, right?
Yeah. Number 8, which is tungsten and cobalt. All right, so thanks for your attention. We ran a little long in the last day, just like we're supposed to. We started a little bit late. Let's go to lab. We're starting with minus 50 points in lab, and you're earning your way to 0 by cleaning up and making sure everything's right before you leave. If you leave without being checked out by one of our designated cleaners, you will lose points today. 50 points.